Thank you very much, Mary. It's a real pleasure to introduce Donald Sadoway. He's known to many of you, I think, from his many activities on the internet and at MIT. He's the John F. Elliott Professor of Materials Chemistry at MIT. He has a very strong connection. He's really home right now. He was born, raised, and went to school all within walking distance of this hotel. It's great to have him here. He is, at heart, I think, a molten salt electrochemist, as am I. There's not very many of these around these days, so it's nice to be able to introduce one. He's extremely well known in the materials chemistry community. He was voted one of the top 100 influential people in the world by Time magazine. His TED Talk on energy storage has been viewed about 1.5 million times, which for our profession is quite amazing. He works primarily in areas of grid-level storage, energy storage, rechargeable batteries, and in sustainable methods for metal production. And he has prepared a really interesting talk that I'm looking forward to on these topics. And without further ado, I'd like you to please welcome him to the stage. Professor Sadoway.
Well, thank you. It is a pleasure to be back here. And be with a few molten salt electrochemists as well. George Kipouros is here, so we've got three. There's three of us. That's a quorum, I guess. Yeah. So I'm going to be professorial this morning. So it's going to be a sort of a mix of lessons and conversations. So the title here is Electrochemical Pathways Towards Sustainability. And of course, yeah. You know, it's always that for a battery person, the battery is going to fail, so that's all right. The subtitle here is the research paradigm shift to cost-based discovery. And if I told you about cost-based engineering and cost-based optimization, you'd say, yeah, well, that's what engineers do. But in the area of metals production and in the area of energy, it's my thesis that you have to think about costs already at the discovery stage. If you leave cost to downstream, you're just not going to have the impact because the entrenched technologies are so difficult to unseat that you really have to think about cost at the early stage. So being a little bit canonical, I'm going to start with what is an engineer? And engineer is, we're having some trouble with this. We need new batteries, I think. According to the Oxford English Dictionary, the engineer is one who contrives, designs, or invents. Designs, contrives, invents, an author or designer. And this is the first use of engineer in the English language, a tower full strong that quaintly engineers made back from 1325. And it would come to you as no surprise that, well, we really need to do something about this, or we're just not going to make it. Yeah. So I actually know what comes next. So the words engineer and ingenious both have the same root. They're both rooted in the same thing. And if we could just get the next slide to go, that would help us. Let's go to the next one. So clear comparison. Just keep hitting it. A scientist discovers that which exists, an engineer creates that which never was. Now let's go to the next one. You see grace under pressure? See, I'm not fazed at all. A scientist converts money into ideas, whereas the engineer converts ideas into money. Well, these are clear comparisons. Okay, let's go to the next one. So now let's get into metal. So that's a little bit of the background about engineering. Let's see if I'm going to be able to. We have some.
We have some new batteries.
We got batteries? Oh, good. Good. No. Well, you know, the issues with metal making are the unfavorable byproducts. So, you know, in case of steel, 1.8 billion tons a year, and we've got carbon dioxide and about a half a ton of carbon to make a ton of steel. And the same thing with aluminum. This is not working. Okay. I don't know. I can't tell if it's me or them, but or maybe it's my hand. Maybe. Oh, now we've got my. Well, that's good. Now we've lost the presentation. That's my car from some. This is actually fiberglass. Oh, now we're back to my talk. This is impromptu. So why is metal production so dirty? Well, I think many of the processes are over 100 years old. And 100 years ago, we had an attitude of indifference to the environment. I remember as a child growing up in Oshawa, one spring, all of the fish were dead because somebody had opened an electroplating shop upstream. And I was with some neighborhood boys, and we just kind of looked at the dead fish and said, yeah, that's too bad. No, nobody was outraged. They just accepted the fact that, well, there's an electroplating shop and the fish are dying. That's the way it was.
They've given their blessing on this one.
Oh, good. Good. Let's see if this one works. Yeah. So this is, you know, where there's smoke, there's money. That was the old attitude. But now we understand things differently, that pollution in one sector eventually gets to another sector. So there's been a change in attitude over time. So being the professor, I decided, well, let's think about this thing canonically. Where do metals come from? Well, they occur naturally as compounds. There's very few metals that are found in the ground as elements. Most of the metals are found in the ground as oxides. We have some sulfides, but mainly as oxides. Then these are beneficiated, eventually up to high purity feed, and then we reduce them. And this is the palette of reducing agents. We use carbon, hydrogen, sometimes another metal, or the electron. And as we've heard, the theme of the conference is sustainability. When I think about sustainability, I think the electron is your most sustainable option, because it's possible to make an electron in a sustainable manner. We don't necessarily have to burn carbon to make electrons. And electron is magical because it only comes in one purity, 100% pure. And, you know, for me, I started off as an electrochemist, but the electricity piece is just becoming more and more dominant. Everything that we value today, what we consider to be 21st century living, is based on electricity. Without electricity, we don't have internet, we don't have anything that we're doing. Communications, information, it's all predicated on electricity. And if you take a look at this image here, you realize this is a collage, right? This is not a NASA image of the world at night, because you know when it's light here, it's dark in Asia. If the world ever looks like this, it's a really bad day for all of us. I hope I never see the world looking like this. And to go back to the professorial piece, let's not forget where electricity began. It began with a professor at the university. This is Volta. And this is his first battery. It's a stack of coins, cardboard soaked in brine, separating, say, silver and zinc. And with it, Volta's invention gave birth to a new field, electrochemistry, but also immediately new technology. It migrated off of campus very quickly. In the early 1800s, we already had electroplating, electroforming, and this served the basis for, once the dynamo was invented and we had continuous electricity, this served as the basis for electrolytic production of metal. It all started here. So Volta's invention gave us new fields of endeavor, but it also did something else. Volta's invention for the first time demonstrated the utility of a professor. Until Volta, no one thought a professor could be of any use. But Volta showed if you give a professor some time and money and leave him alone, he's liable to do something that has some value for society. And that's why we have sponsored research to this day, because of what Volta did. So I'm happy to be following in his shoes. So what are the requirements of a new extraction technology? Well, it's got to reduce the environmental impact. It's got to reduce production costs, both capital costs and operating costs, provide flexibility in raw materials, and it's got to improve quality. It's got to do everything. Nobody wants a more environmentally sound process, but the metal is a little bit inferior. That's not going to work. So I'm going to tell you a little bit about molten oxide electrolysis, which I invented at MIT some time ago. So, I've told you that most metals are found in the ground as oxides. It's my thesis that the electron is the best reducing agent, and from teaching for many years freshman chemistry at MIT, I've come to appreciate that like dissolves like. So oxides, electron, like dissolves like, that means molten oxide electrolysis. And that's an extreme form of molten salt electrolysis, but we're going to go to higher temperatures, and we're going to make oxygen as the byproduct. So here's what the cell looks like. It actually looks a little bit like a Hall cell. You've got an anode at the top, cathode at the bottom, metal oxide feed dissolving in the oxide melt here. And by the action of electric current, we generate joule heat, which keeps this thing molten. You cool a Hall cell, you don't heat a Hall cell. And you got frozen electrolyte on the side, oxygen coming off the top, metal pooling at the bottom. So in case of iron, you'd make liquid iron at the bottom and oxygen at the top. So, when I first started talking about this, people said I was crazy. But this would give you a lower capital cost per cell. If you tried to build a greenfield integrated steelworks today, you'd have to come in at several million tons at several billion dollars. And that's a lot of money. And it's not going to happen. Very rare to see new integrated steelworks. This capital cost is about 20 times lower. And that gives you a minimum production capacity, lower barrier to entry. And finally, the same feed supply chain. So you don't need a center plant, you can use big chunks, you can use fine particles, doesn't matter at all, it's going to melt anyways. And this is kind of interesting because you look at the environmental attributes. Obviously, if you had electricity generated by nuclear or hydro, your carbon footprint would be tiny. But the thing that surprised me, that red line is a benchmark of a pretty good blast furnace. It's about 2 tons of carbon dioxide per ton of iron. That third line, that third bar, is the case of gas-fired electricity. So if you took natural gas, made electricity, and then electrolyzed iron oxide, your carbon footprint would be still lower than in a blast furnace. Obviously, if you burn coal, that doesn't make much sense. So the other thing is energy consumption is about 25% lower than that in a blast furnace because the electron is acting as both your fuel and your reductant very efficiently. Now, it's at the university, and I'm obliged to do things academically, so what I tell my sponsor is we're going to invent a new process to make iron, but the thesis has to have a title something like electrical conductivity of molten ferrites. So we got the both sides coming. So the molten oxides of transition metals are electronic conductors, and so there's been a lot of work to try to control the conductivity mechanism, and obviously coming up with an inert anode that can operate at 1700 degrees Celsius in an oxide melt. That's taken some time, but we've got it. So here's some examples of electrolysis. This is about 3-inch diameter molybdenum crucible, and that was iron that was made by direct electrolysis. Perfectly clean iron. The carbon content would be less than 25 parts per million. And the current density was about 1 amp per square centimeter, which is about 20% higher than that of a Hall cell. Here's some more, and I swear that's iron. I did not use crazy glue to tape that on there. This will give you an example of an inert anode operating. You'll see at the positive electrode oxygen coming off. It's a melt containing iron oxide, silica, alumina, and you'll see it's somewhat viscous, but it's definitely operating very much like a molten salt. We've also looked at nickel. Some nickel is found as oxide. We were able to make nickel very easily. Chromium melts at 1900 degrees. That's a little bit too high for the furnaces that I have. So we started with iron in the heel, made ferrochromium. So this is carbon-free ferrochromium in one step. So I've shown you carbon-free iron, carbon-free nickel, carbon-free chromium. That means I could make virgin stainless. Manganese, it melts at 1240, so this is child's play for us, and it was easy to make manganese. And that's manganese oxide going to manganese in one step. This is a little bit of electrochemistry, Boyd. So this is some cyclic voltammetry in molten titanates, just to make people a little bit uncomfortable. And then we'll show them a picture of some titanium. And so this is titanium made in one step. So there's no Kroll process, no carbochlorination. This is titanium oxide dissolved in an all-oxide melt. We ran this cell at 1725 and made liquid titanium. And now we're looking at rare earths. That's me looking down in there, see what's going to happen. And this is the inert anode. It's not made out of rhodium or something like this. It's a ferrochromium alloy that forms a passivating surface and allows us to pass current at an acceptably low resistance. And you can see this thing after several hours, it's still intact. And this was published in Nature. I've got tenure. Tenure means never having to say you're sorry. But I do publish because it's important to launch the careers of the young people. And Nature, it's really tough to get published there. And when it comes to metallurgy, they publish about one paper in a decade on extractive metallurgy in Nature, and this was it. So I'm very happy for the two young people. Antoine is now a professor at MIT, and Lan is a professor at Tsinghua University in China, which is one of their top schools. So I've shown you this, not a process, but a platform. Many metals can be made by this option. So what do we got here? Well, we wanted to go to a self-heating reactor because our cells on campus require external heat. So we have to go to a finite size before we have self-heating. And for that, we had to go off campus. We started a company, Boston Electrometallurgical. We've got 6 people working at about a 6,000 square foot facility in Woburn. And we've designed and built a cell that's 1,000 times that. It's about 1 meter in diameter. And it operates at temperatures as high as 1900 degrees C. And we'll have pilot scale production by the end of this calendar year. And this will give you a sense of this. So that's about 1 meter in diameter, and the image is a little bit dark, but this is a human form here. This is the hand. You can see he's looking at the tap hole here, and he's got the shroud on and whatnot. So that gives you a sense of the scale here. And this is over 1600 degrees C. And this is operating in a continuous fashion. And we've made hundreds of kilograms of metal, not hundreds of grams, hundreds of kilograms of this stuff. So this thing really has legs. Now I'm going to switch to the other part. So I'm giving you a little vignette about the molten oxide electrolysis. Now I want to go over to liquid metal battery. And I've made the point about electricity and modernity. And you see on this collage, there are some areas that are dark. Now, they're dark for one of two reasons. Either nobody lives there or the place hasn't been electrified yet. And if we want to get the last 2 out of 7 people on the planet electrification so that they can participate in the modern world, we don't have to connect them to the grid. We can just drop in solar or wind with storage, and then we will have sustainable electricity to give us a sustainable modernity. That's the real challenge for us. So storage to me is the big missing piece, and it's not only for renewables. The grid today, it's the largest supply chain in the world with 0 inventory. So imagine if we had water the way we have electricity. Electricity demand must be in perfect balance with supply everywhere at all time. And if we had water that way, every time you open the faucet, it comes from a spring, goes through the pipes, there's no tank. And if you close that faucet, they got to damp down the spring. Otherwise, if you keep pouring water into the pipes, the pressure builds up. The same thing happens with electricity. The voltage will migrate, the frequency will migrate. You know what's worse than no electricity? Bad electricity. If every time you plugged your device in, you had to say, "Do you feel lucky?" And then the other crazy thing is the grid is designed for peak load. Imagine if we built the Gardner Expressway for peak, so you never had to hit the brakes. It'd be 20 lanes wide in each direction. You'd say that's crazy. Well, that's the way the grid is. It's designed for peak load, and we'll hit that maybe less than 5% of time. And the difference is about 40% peak over average. And the estimate is to electrify the rest of the world is going to take about $17 trillion over the next 20 years. And if 40% of that is just wasted, that's $7 trillion that could go into education, healthcare, what have you. And renewables, right now renewables get a free pass because they're down below 5%, so if the sun comes in, who cares? But you start getting renewables up at 15, 20% of the total value, and you're going to have huge problems. You know, because you have to keep supply and demand in balance. If I give you solar energy at zero marginal cost, and you don't have the demand, that's a problem. It's not a solution. But if you had storage, then you'd be able to draw electricity from the sun when the sun doesn't shine, and solar then can become part of base load. So that's sort of my inspiration. You say, well, it sounds like you made a good case. Why don't we have these batteries? And the answer is cost. And this is a graph. It's a semi-log plot. So that means all of these things are less than 0.1%, which means nothing. And the only thing that works is pumped hydro. But pumped hydro is geographically constrained. You can't put pumped hydro in downtown Toronto. And even if you wanted to put it someplace in the hills, you're going to have trouble getting permitted today because today's public doesn't have the appetite for messing with nature. So it's not going to happen. And the other thing that I get from this plot is that if I don't get below $500 a kilowatt hour, I probably aren't going to have any impact. So that means cost is really the driver here. So it's not battery versus battery, it's battery versus combustion. And you know, I got to compete against diesel gensets, natural gas, and you got to think differently. You're not going to take a battery that can power this and scale it up by 100 times. That's not going to get you there. You got to think differently. So these are my two ideas. One is confine the chemistry to earth-abundant elements. Well, this is a plot of earth abundance, and it's also a log plot. So that means these elements up in the top left corner are a billion times more abundant than those elements in the bottom right corner. And that means to me, if I'm going to work on a battery, I forbid my students to work in that bottom right corner. It's wasting your time. You see, platinum is down there. That's why we don't have hydrogen-powered vehicles, because platinum is so scarce. And tellurium is down there, and I don't know why people work on cadmium telluride solar cells. If I gave you tellurium for free, it just doesn't exist. So you better work in the upper left corner. So I say if you want to make something dirt cheap, make it out of dirt, and preferably local dirt. Because it doesn't make sense to trade in your dependence on imported petroleum for dependence on imported neodymium. Your dollars are leaving the country. It doesn't matter what. And the other thing is make it easy to manufacture. You want a primitive process, really simple. So when I started working on this problem about 10 years ago, first thing I did is I disregarded everything I knew about batteries. And I looked for inspiration elsewhere. I looked to metallurgy. Because I knew about an aluminum smelter. I knew an aluminum smelter, whoops. You take bauxite from one corner of the globe, petroleum coke, 13 kilowatt hours of electricity make a kilogram of metal. and $5,000 a ton capital cost, and yet you go from dirt to metal for less than 50 cents a pound. That's an economic miracle. And it consumes huge amounts of energy, electrical energy. And I reasoned if I could just teach that cell to not drink the power, but to hold it and give it back, I knew that at the end of the day, I'd have something that was cheap because 50 cents a pound to make metal. And here's a modern smelter. You know what this is. It goes back a couple of kilometers, whatnot. Invented in 1886 by Hall in the United States and Heroul in France. There they are. They're both born in the same year. They both died in the same year. They met once, 1911 at Philadelphia at the American Chemical Society when Heroul was given the Perkins Medal and Hall was given the Perkins Medal, and Heroul came from France and spoke in tribute. They were fierce competitors, but they admired each other and they respected each other. Well, they were both born in the same year. I guess they must have been the same age in 1886. Guess how old they were? 22. 22. Two 22-year-olds changed the world. They took aluminum and turned it from a precious metal costing more than silver into a common structural material. But that's because aluminum is the third most abundant element in the Earth's crust. If they'd invented this process for rhodium, it wouldn't have made any difference. So abundance really counts. So that was the basis for this invention of the liquid metal battery. We had a little bit of internal funding at MIT. If I'd written this up and sent it in for a proposal to the Department of Energy, it would have been thrown out. I said it was crazy. But so we've got 3 layers, liquid magnesium on top, liquid antimony on bottom, and molten salt in between. The magnesium's insoluble in the electrolyte's insoluble in the antimony. They separate, there's no need for a barrier, there's no membrane. And then to discharge, well, this is my team, by the way. Who did I choose? I chose David Bradwell. He's also from Toronto. He got his bachelor's degree in physics from Queen's University. Didn't have any background in batteries, no background in electrochemistry. He looks really worried in this picture. He's wondering if this thing's going to work. What I didn't tell him is I wasn't sure it was going to work either, but I mentored him. How did I mentor him? I said, oh, it's going to work. And he made it work. Now, the American Chemical Society was doing a profile on me a few years ago, and they wanted a picture. And I sent them this image, and they refused to publish it because we weren't wearing goggles. And I said, it's just a staged picture. It's not real. And they said, we will not show a professional in a setting, a laboratory setting, dressed unprofessionally. I said, why don't you just take out a Sharpie and put the goggles? And they have no sense of humor, American Chemical Society. So I had to find another image. So anyways, this is how the battery works. The magnesium wants to alloy with the antimony, and so it dissolves as an ion. Electrons go through the external circuit, and then the bottom layer gets deeper and the top layer gets shallower. And then to charge it, you're essentially electrorefining magnesium out of the antimony, so you're purifying all the contents. And that purification step is key to the longevity. And as you're drawing current, whether you're charging or discharging, you're generating joule heat. And then you trap that joule heat, and this thing can stay molten for several days. So if you operate it on a daily basis, it's fine. And people say to me, oh, well, you're going to lose all of your energy just generating heat. No. The round-trip efficiency is 75%, which is comparable to pumped hydro. That's after paying for the heat. It's because those of us who know molten salt chemistry know that it doesn't take a lot of energy to keep things at that temperature. And then my fortunes changed. I had a chance to give a talk in Paris, and Total came up to me and said, what would it cost to build one of these things for a home? Because Total was starting to get interested in solar energy, and they knew solar without storage wasn't going to be complete. And I knew they were an oil company, so I blurted out, oh, $4 million, and they said, fine. And then the ARPA-E was formed in 2009, and I was a first-round winner of an ARPA-E grant. And with that money, my group looks like this now. And again, you know, there's 20 people here, and no battery people. No battery people. The only guy that knows batteries is the guy in the bottom left, and he's a little bit of a maverick anyway. But this group of people with fresh ideas and passion, they were fantastic. But initially, our work was not succeeding. And we were visited frequently, about every 3 months, by the Department of Energy. And after the third meeting, Dave Danielson, who's now the Undersecretary of Energy, he was our contract monitor. We were showing our poor results, and he stood up and said, of all of the projects in my portfolio, he had about a half a dozen of them, he says, I give this one the least chance of success. Then he left. And you know, the hearts sank. But I mentored them. And 2 years later, they'd worked miracles. This is a multinational strike force, diverse, Spain, Korea, China, France, Trinidad, Polynesia. He's from Tahiti with a PhD in high-energy physics in Paris. Poland. David and I, both from Canada. And I hired a couple of token Americans, too. You know. And what I learned from this is the big group is really valuable. They learn from each other. So 20 times 3 is way greater than 3 times 20. If I had the same amount of money spread over 20 years, I wouldn't be standing here right now. So we've tested over 1,000 cells, different combinations of alloys and salts. And you know, this is one of the times we're dealing with the liquid state, and all the ab initio calculations, density functional theory, all that great stuff, it can't help us. We have to go and measure this. Sometimes there aren't even phase diagrams, or worse yet, the phase diagrams are inaccurate. And this one got published in Nature late last year, and again, launched the careers of people. But this is the thing that really makes this exciting for me. This is a battery that's been operating at 93% depth of discharge, so from full charge almost to full discharge. This is a very strong stress test. Fade rate is 0.00009% per cycle. What's that mean? It means if you cycle this thing once a day for 10 years, that's 3,650 cycles, 99.7% retention of original capacity. There's no battery on the planet that can do that. The normal metric is how long does it take to drop to 80% capacity? In this case, 607 years. As I look around this room, I think that ought to pretty much take care of everybody's needs here. Right? Maybe your grandchildren. So we started a company to get it off campus, and all the cute names were taken. So we had this really boring name. If you want me to give you if you want a boring name for a company, call me. I can give you one. Liquid Metal Battery Corporation. And then a couple of years ago, we renamed it Ambry because we invented it in Cambridge. So Ambry is out of the heart of Cambridge. And my first funding came from Bill Gates. Now, I'm Canadian. I'm polite. I wouldn't dare approach Bill Gates. He came to me. Why? Well, I was teaching this big freshman chemistry class, and I had more than 2/3 of the freshmen at MIT taking my class, and it was too big to fit in a room. So they were recording the lectures, and eventually they put them on the internet starting around 2004. And turns out somebody pointed out to Bill, I must have said something about batteries. He looked at one of my lectures. Next thing you know, he's watched all 35 of my freshman chemistry lectures and is recommending this to people at Microsoft. So I get an email one day in August of 2009 from a woman who says she's his secretary and he'd like to come to Boston. Would I be available for 90 minutes to meet with him? Well, I disregarded the email. I thought the students had hacked into my account. I thought they were just going to make a fool out of me, so I didn't answer. So then about a week and a half later, she wrote again and says, perhaps you didn't see my email, but I'm serious. He really wants to come to see you. Well, I said, okay, maybe this is real. So yeah, he came and we chatted in my office. We talked about chemistry, engineering education, distance learning, and then somehow we got on the topic of batteries. This was 2009, before the ARPA-E money and so on. David and I had nothing in the way of results. And I go to the whiteboard and I sketch this stuff out, and he says to me at one point, if you ever decide to spin this out as a company, let me know. I'd be willing to put some money into it. And a year later, David and Louis Ortiz approached him, and he was our first investor. So this is a story I can tell in mixed company. I met Bill Gates not because I was quoted in the Wall Street Journal. I met Bill Gates because I was teaching freshman chemistry, which is something most of my colleagues would kill to avoid. They don't want to teach big classes. They want to teach tiny classes in their specialty. We're going to read my former papers, and we're going to call that a class, and so on. I didn't do that. I went for big impact, and it paid off. And then Total matched Bill. They were a French oil company, right? And they wanted to really put the screws down. But Bill gave us really good terms. And I said, well, you can't insult Bill. You have to match Bill's terms. So that worked out well. And then we had, of course, to invent everything, because we had to invent the battery management system, the power electronics, and so on and so forth. And so here we are with, this is the former governor of Massachusetts, at a ribbon-cutting ceremony for a manufacturing plant just outside of Boston. So here we are. This would be the 53-foot trailer on an 18-wheeler. That's the footprint of this. This is 1 megawatt hour. Silent. The sound of electrochemistry, right? Emissions-free, not like diesel gensets. No moving parts, not like flow batteries. Remotely controlled. So this can act as a sink as well as a source. And here in Ontario, sometimes you get negative pricing because there's a superabundance of electricity. And you got to balance supply and demand. So you call people up and say, please turn on your machinery. Well, this thing can, in a millisecond, can turn from a load into a source. And it's designed to the price point of the market without subsidy. So where are we? This is the only graph that counts in everything I've shown you, right? Well, obviously, the first one is going to be way off to the right, but our models indicate that we're going to be below $500 a kilowatt hour at scale. The first ones, of course, are going to be expensive, but at scale, we think we can get there. So what have I learned from all this? What have I learned? Temperature. Everybody told me, batteries, you got to run them at room temperature. I said, nah, make them high temperature. I don't have any membranes, self-segregating. Scaling. You see, you want to scale, make many. I said, no. Make fewer, make them bigger. You can be too big to succeed. Too big to succeed. Human resources. Oh, get the experts. I say, no, I don't want the experts. I want the novices. I want bright young people who are unjaded, who are fearless, who don't know things are impossible. And it's all about the culture of the group, too. You can have the strategy, but if you've got a toxic culture, you're not going to prove anything. See, this is a guy talking to his cat. Never, ever think outside the box. If you have a culture like that, you're not going anywhere. And then, in terms of global dissemination, the idea is to be localized. Batteries in Canada should be made by Canadians using Canadian resources, not everything made at one company in China and shipped all over the world. That way, Canadians become authors of their future. So I'm going to end by going back to some professorial stuff. And, I think a lot about the inventive process. How do we teach creativity? I mean, I can teach you content backwards and forwards, but how do I ignite that spark? And you go to all these business schools and they teach you all. The only thing you learn at business school is that no case is the same as the other. So you can look at all the other cases, but your case is different. It doesn't matter. So I heard this talk by someone at TED. The miracle of your mind is not that you can see the world as it is. I mean, a dog can see the world as it is. The miracle of your mind is that you can see the world as it isn't. You have that capacity if you allow yourself. You can see the world as it isn't. You can imagine the future and you can remember the past. And you put all those ideas together and you can create. And you can imagine being some other person in some other place at some other time. And that's what fuels me, that irrepressible ability in young people. That's why I applaud Mary's interest in taking that gap and mentoring the emergent professionals, because that's where the best ideas are going to come from. All right, so what I tell my students is the battle cry from Paris 1968. Be realistic. Ask for the impossible. And you know, sometimes with enough ingenuity, the impossible becomes the inevitable. Thank you.
Thank you very much for that really inspirational talk. I think we have time for a few questions if there are any in the audience. Phil? I think there's a microphone right there if you want to.
Dr. Sadoway?
Yeah.
It's Philip Mackey. I echo Mary's comments, very inspirational, and wish you all the best. In this new system, we will of course need to conduct the electricity. Therefore, we will need the metals like, for example, copper and the aluminium you mentioned, maybe nickel. So what are your thoughts on taking those ideas as to how these metals should be produced in future to, you know, conduct the electricity that is, as you say, the future?
Well, I mean, for me, the bluest sky image of the future is producing those metals in a sustainable manner, which is, to my mind, electrolytically, where the electricity is generated by sustainable means, photovoltaics or wind, hydroelectric. And so whatever you need by way of conductors, you're going to generate in a sustainable manner. Parenthetically, you know, the connections on these cells at elevated temperature, our battery right now is running at about 500 Celsius. You can't use copper at 500 Celsius in open air. So we've been working with aluminum bronzes, copper with aluminum added to it that forms a surface film of aluminum oxide. And so there's this constant back and forth of necessity, invention, and it's very rich. It really saddens me that in the last days of the 20th century, so many material science departments were phasing out metallurgy. You know, they wanted to embrace nano, bio, and all this stuff, and fine, okay, but you don't get rid of steel making because someone discovered a nanotube. And yet people said, well, this is a mature industry. When I was coming up for tenure, the dean of engineering was sitting across from the head of the material science department, it was Mert Flemings at the time, and was grilling Mert about, why do you want to tenure this guy? It's 1984, and he's working on aluminum. I was doing molten salt electrolysis and Raman spectroscopy and molten salt cells, and he was looking at me as though I was working on something from the 19th century. So they're wrong. There's lots to discover. Lots to discover. And I mean, I put my money on metal before I put my money on graphene.
I think it behooves us all to re-educate the public about the role metals plays in it, so. I think we're going to have to end it there to move on to our next plenary speaker, but Professor Sadoway will be around today, at least in attending a few of the talks, so thank you again very much. So.